Welcome to today's session. We're going to tackle an interesting problem from LeetCode, problem number 382, linked list random node. This problem is a great way to deepen your understanding of probability, linked lists, and how to handle randomness effectively in coding. Let's dive right in. Here, we are tasked with a problem involving a singly linked list. Each node in this list contains an integer value, and our goal is to implement a solution that can randomly select a node's value. The key requirement is that each node in the linked list must have an equal probability of being chosen. To achieve this, we need to design a solution class. The class will be initialized using the head of the singly linked list, which represents the starting point of the list. Once initialized, we will implement a method called getRandom. This method will return a randomly selected node value from the linked list, ensuring that each node's value has the same probability of being selected. This setup forms the foundation of the problem, and it's important to maintain fairness in the random selection process. The getRandom method can be called multiple times, and each invocation should return a randomly selected value from the linked list. The output of this method is expected to be an integer, representing the value of one of the nodes in the list. To better understand how this works, let's look at an example. Suppose the linked list contains 3 nodes with values 1, 2, 3. When we create a solution object using this list and call getRandom, it could return any of these values, 1, 2, or 3. Importantly, each of these values must have an equal probability of being returned. This means that over many calls to getRandom, the distribution of returned values should be uniform, with each value appearing approximately 1/3 of the time. Now, let's consider another example where the linked list contains 4 nodes with values 4, 7, 9, 10. When we initialize a solution object with this list and call the getRandom method, it could return any of the values 4, 7, 9, or 10. Each of these values must have an equal chance of being selected, which in this case is a 1/4 probability for each value. The concept remains the same regardless of the size of the linked list. The goal is to ensure that the random selection is fair and that all node values are equally likely to be returned. This example illustrates how our solution must handle lists of varying lengths while maintaining uniform probability distribution. To meet the problem's requirements, we must consider several constraints and edge cases. First, the linked list can have up to 10⁻4 nodes, and each node's value can range from -10⁻4 to 10⁻4. Additionally, the getRandom method may be called up to 10⁻4 times, so our solution must be efficient and scalable to handle these scenarios. For edge cases, if the linked list contains only one node, the getRandom method should always return the value of that single node. For larger linked lists, the solution must ensure consistent and uniform probability distribution even with repeated calls. By addressing these constraints and edge cases, we can ensure that our solution performs robustly under all conditions. To tackle the problem of selecting a random node from a linked list, one initial approach we could consider is the brute force method. The intuition behind this approach is straightforward. We traverse the entire linked list and store the values of all the nodes in an array. Once we have the array, we can use a random number generator to pick an index within the range of the array size. By returning the value at that index, we ensure that each node has an equal probability of being selected, thanks to the uniform randomness of the selection process. However, while this approach is simple and easy to understand, it comes with trade-offs. It has a time complexity of O(n) during the initial traversal and O(1) for random access, but the space complexity is also O(n) due to the array. This extra space requirement makes it inefficient for very large linked lists, as it requires us to store all node values in memory, which can be a significant drawback in resource-constrained environments. Now, to address the limitations of the brute force method, we can use an optimized approach called reservoir sampling. This algorithm is designed to select k items from a data stream, or in our case, a linked list, without needing to know the total size of the data beforehand or storing it in memory. The steps are as follows. As we traverse the linked list, we maintain a count of the nodes visited so far. For each node, we decide whether to select its value based on a random probability. Specifically, we replace the previously selected value with the current node's value with a probability of 1 divided by the count of nodes visited. This ensures that each node has an equal chance of being selected. By the time we reach the end of the list, the last selected value is returned. The key advantage of this algorithm is that it guarantees uniform randomness while using constant space, as it only keeps track of the current count and the selected value. This makes it a highly efficient solution for large linked lists, with a time complexity of O(n) and a space complexity of O(1). Reservoir sampling stands out for its space efficiency and its ability to handle very large linked lists seamlessly. Unlike the brute force method, it does not require storing all the node values, making it an excellent choice when working with memory constraints. However, it is slightly more complex to implement compared to the brute force approach. After considering both methods, reservoir sampling emerges as the superior strategy for this problem. Its O(1) space complexity is a significant advantage, especially when the linked list size is too large to fit into memory. Moreover, it mathematically guarantees equal probability for each node's selection, which is critical for the correctness of the solution. The realization that we can achieve uniform randomness with just one pass over the list in constant space was a pivotal insight. This eliminates the inefficiency of storing additional data while maintaining the desired result. When we compare the two approaches, brute force is undeniably easier to implement, but its high memory usage makes it unsuitable for large linked lists. On the other hand, reservoir sampling is more space efficient and scalable, making it the better choice overall. Its ability to work seamlessly with very large datasets while maintaining correctness and efficiency makes it the optimal solution for the linked list random node problem. In conclusion, reservoir sampling strikes the perfect balance between space efficiency, scalability, and mathematical correctness, making it the preferred strategy for this problem. This problem asks us to implement an algorithm for selecting a random node from a singly linked list, ensuring that every node has an equal probability of being chosen. The challenge lies in the structure of a linked list, which does not support direct indexing like an array. Consequently, we can't access nodes based on their positions efficiently. A straightforward solution to this is the brute force approach. The intuition here is to traverse the entire linked list and extract all node values into an array. Once we have the array, we can easily select a random value by generating a random index, ensuring uniform probability. To achieve this, we start by initializing an empty array called values. As we traverse the list, we append the value of each node to this array, moving from the head node to the end of the list. After populating the values array with all node values, the next step is to randomly select an element. We generate a random indexer between 0 and len values, one using a uniform random number generator. This index corresponds to a random node in the linked list, and we simply return the value at values, r. While this approach guarantees uniform probability, it has notable computational costs. The time complexity is O(n) for traversing the linked list and populating the array, with an additional O(1) for the random selection, making it O(n) overall. However, the space complexity is also O(n), as we allocate extra memory for the array. This additional space can be inefficient, especially for large linked lists, which is why we explore a more optimized approach next. To address the space inefficiency of the brute force method, we turn to an optimized solution called reservoir sampling. This approach eliminates the need for extra storage by making probabilistic decisions during the traversal itself. As a result, it ensures uniform probability for all nodes without requiring additional space. The algorithm begins by initializing a variable called reservoir, which will store the randomly selected node's value. Initially, reservoir is set to none. We also initialize a counter n to track the current node's position in the traversal, starting from 0. With these variables ready, we start traversing the linked list. For each node encountered, we increment n by 1. Then, with a probability of 1/n, we update reservoir to the current node's value. This probabilistic update ensures that every node has an equal chance of being selected. After this step, we move to the next node in the list. Once the traversal is complete, the value stored in reservoir is our randomly selected node value. The key insight behind reservoir sampling lies in its probabilistic fairness. At any step I, the probability of selecting the current node is 1/i. Additionally, the probability of that node remaining chosen through subsequent steps is calculated as 1/i asterisk I plus 1 I plus 1 /i plus 2 asterisk which simplifies to 1/n for a list of n nodes. This ensures uniform selection across all nodes. Compared to the brute force approach, reservoir sampling offers significant advantages. It is highly space efficient, using only O1 space since we don't store all node values. This makes it particularly suitable for very large linked lists where storing all data is impractical. The algorithm also handles edge cases effectively. For example, in a single node list, it will always select that node, and for an empty list, it can return null or handle the situation as needed. When comparing the data structures and complexity of the two approaches, we see clear differences. In the brute force method, an array is used to store node values temporarily, making random access straightforward but requiring O(n) space. In contrast, reservoir sampling uses a single variable, reservoir, to store the random node value, ensuring O(1) space usage. In terms of complexity, both approaches have a time complexity of O(n), as they involve a full traversal of the linked list. However, the brute force method has a space complexity of O(n), while reservoir sampling is far more efficient with O(1) space. This makes reservoir sampling the preferred solution for this problem, particularly when working with large linked lists where memory usage is a concern. This solution involves implementing a random node selection from a singly linked list using reservoir sampling. The reservoir sampling technique ensures that each element in the linked list has an equal probability of being selected, even with an unknown or dynamically changing size. First, the solution class is initialized with the head of the linked list. The head is stored as an instance variable for use in the getRandom method. The getRandom method is where the random selection happens. A variable reservoir is initialized to store the selected node's value. It starts with a placeholder value of -1. We also define a current pointer for traversing the linked list and an index variable to keep track of the position of the node being processed. The algorithm iterates through the linked list using a while loop until the end of the list is reached, current becomes none. For each node, we decide whether to replace the value in reservoir with the current node's value based on a random decision. Specifically, we generate a random integer between 0 and index, inclusive. If the result is 0, the reservoir is replaced with the current node's value. This ensures that each node has a 1/index plus 1 chance of being selected, maintaining uniform probability across all nodes. Finally, the index is increment, and the current pointer is moved to the next node in the list. After the loop completes, reservoir contains the value of the randomly selected node, which is then returned. This approach has a time complexity of O(n), where n is the number of nodes in the linked list, because we traverse the list once. The space complexity is O(1), as we only use a few variables for the algorithm and do not require additional data structures. This makes the solution efficient and well suited for the problem's constraints. Here, we begin by defining the structure of a singly linked list with the listNode class. Each node contains an integer value, val, and a reference to the next node, next. The constructor initializes these values when a new node is created. Then, we have the solution class, which is designed to work with the linked list. The solution class has two private fields, head, which stores the reference to the head of the linked list, and random, an instance of the random class used for generating random numbers. The constructor of the solution class initializes these fields, setting up the linked list and preparing the random number generator for later use. The key method we're implementing here is getRandom, which is tasked with returning the value of a random node from the linked list. To achieve this, we use a technique called reservoir sampling. At the start of the method, we declare an integer variable reservoir initialized to -1, which will eventually hold the value of the randomly selected node. We also set up a current pointer to traverse the list and an index variable to keep track of the position of the current node as we iterate through the linked list. The getRandom method continues by iterating through the linked list using a while loop. Inside the loop, for each node, we decide whether to replace the current value of reservoir with the value of the current node. This decision is made using a random number generator. Specifically, we replace the reservoir value with the current node's value with a probability of 1/index plus 1. This ensures that each node in the list has an equal probability of being chosen, regardless of the size of the list. The random.nextInt, index plus 1, generates a number between 0 and index, and if this number is 0, the reservoir is updated to the value of the current node. After evaluating the current node, we move the current pointer to the next node and increment the index by 1. Once the loop completes, meaning we've traversed all the nodes in the list, we return the value stored in reservoir. This implementation of reservoir sampling ensures that the selection is truly random and efficient, as it only requires a single pass through the linked list, making it ideal for situations where the size of the list is unknown or very large. Let's start with example 1, where we have a linked list containing the values 1, 2, and 3. Our goal is to randomly select a node, ensuring that each node has an equal probability of being chosen. Initially, the head pointer is set to the first node with a value of 1. To begin the getRandom function, we initialize 3 variables. Reservoir is set to -1, which will store our randomly selected value, current is set to head, pointing to the node with value 1, and index is set to 0 to keep track of the position in the list. In the first iteration, the current node value is 1. We generate a random number in the range 0, 0, which results in 0. Since this random number equals 0, we update reservoir to 1, the value of the current node. Then, we move the current pointer to the next node in the list, which has a value of 2, and increment index to 1. In the second iteration, the index is now 1, and the current node value is 2. We generate a random number in the range 0, 1, and this time, the result is 1. Since the random number does not equal 0, the reservoir remains unchanged at 1. We then move the current pointer to the next node, which has a value of 3, and increment index to 2. Now, in the third iteration, the index is 2, and the current node value is 3. We generate a random number in the range 0, 2, and the result is 0. Since the random number equals 0, we update the reservoir to 3, the value of the current node. Finally, we move the current pointer to none, indicating the end of the list, and increment index to 3. At this point, the function returns the value stored in reservoir, which is 3. Now, let's move to example 2, where the linked list contains the values 10, 20, 30, and 40. The head pointer is initially set to the first node with a value of 10. Similar to before, we begin the getRandom function by initializing reservoir to -1, current to head, and index to 0. In the first iteration, the index is 0, and the current node value is 10. We generate a random number in the range 0, 0, resulting in 0. Since the random number equals 0, we update reservoir to 10, the value of the current node. We then move the current pointer to the next node with a value of 20 and increment index to 1. For the second iteration, the index is now 1, and the current node value is 20. We generate a random number in the range 0, 1, and the result is 1. Since the random number does not equal 0, the reservoir remains 10. Next, we move the current pointer to the node with value 30 and increment index to 2. In the third iteration, the index is 2, and the current node value is 30. We generate a random number in the range 0, 2, which results in 2. Again, since the random number does not equal 0, the reservoir remains 10. We then move the current pointer to the next node with a value of 40 and increment index to 3. In the fourth iteration, the index is 3, and the current node value is 40. We generate a random number in the range 0, 3, and this time, the result is 0. Since the random number equals 0, we update reservoir to 40, the value of the current node. Finally, we move the current pointer to none, signaling the end of the list, and increment index to 4. At the end of this process, the function returns the value stored in reservoir, which is 40. Finally, let's look at example 3, where the linked list contains only one node with the value 5. Since there's just one node, the head pointer is set to this single node. As usual, we initialize the variables. Reservoir is set to -1, current is set to head, and index is set to 0. In the first and only iteration, the index is 0, and the current node value is 5. We generate a random number in the range 0, 0, which results in 0. Since the random number equals 0, we update reservoir to 5. After this, we move the current pointer to none, marking the end of the list, and increment index to 1. With no more nodes to process, the function returns the value stored in reservoir, which is 5. Let's begin by analyzing the time complexity of this solution. When we initialize the class using the __init___ method, we simply store the reference to the head of the linked list. This is a straightforward operation that involves assigning a pointer. Since no iteration or additional computation is required, the time complexity here is 1. Now, for the getRandom method, it employs the reservoir sampling algorithm to select a random node from the linked list. The core of this method lies within a while loop that traverses the entire linked list. Suppose the linked list has n nodes. In each iteration of the loop, generating a random number with random.randint, performing a comparison, and potentially updating the reservoir all take constant time, or 1. Similarly, moving to the next node is also an 1 operation. Since the loop iterates exactly once for each of the n nodes, the overall time complexity of the getRandom method becomes n. Now let's consider the space complexity. For the __init___ method, the constructor only stores a reference to the head of the linked list. As this involves a single pointer, the space complexity is 1. For the getRandom method, it does not require any additional data structures. Instead, it uses only a few variables, an integer reservoir to store the random node's value, a pointer current to traverse the linked list, and an integer index to track the current iteration number. Since all of these are simple variables, they collectively consume constant space, or 1. Additionally, because the algorithm does not create a copy of the linked list or modify it in any way, the overall space complexity of the method remains 1. Next, we can analyze the best, average, and worst-case scenarios for this algorithm. In the best case, the linked list contains only one node, meaning n equals 1. Here, the getRandom method completes in 1 time since the while loop executes only once. For the average case, the linked list has n nodes, and the algorithm will always traverse all n nodes regardless of the random selection, making the average time complexity n. Similarly, in the worst case, the linked list also has n nodes, and the algorithm still traverses all n nodes, so the time complexity remains n. Let's also compare this approach with a naive solution. A naive method would involve two steps: first, traversing the entire linked list to store all node values in an array, which takes n time, and second, selecting a random value from the array in 1 time. However, this naive approach requires n space for storing the node values in the array, which is less efficient in terms of space usage. The reservoir sampling algorithm offers a significant improvement over the naive approach by eliminating the need for additional storage. Instead of storing all node values, it selects the random node during the traversal itself, which reduces the space complexity to 1. In terms of time complexity, both the naive approach and reservoir sampling require n time due to the traversal of the linked list. However, the space complexity of reservoir sampling is superior, as it achieves 1 compared to the n space used by the naive method. To further solidify this, the mathematical proof confirms that the while loop in the getRandom method iterates once for each node and performs constant time operations per node, such as random number generation and comparison. Thus, for n nodes, the total time complexity is n. Since no additional data structures are used, the space complexity remains 1. This makes the reservoir sampling algorithm both time-efficient and space-efficient for this problem. When working on problems like linked list random node, there are some common mistakes to avoid. First, not handling edge cases properly can lead to runtime errors. For example, an empty list or a list with only one node may not be explicitly accounted for, so it's important to validate inputs and test these edge cases. Next, storing all the nodes in an array for random selection might seem intuitive, but this introduces significant memory overhead. It requires n extra space, which can be problematic, especially for very large linked lists. Another mistake is retraversing the entire list every time a random value is needed. This approach results in n time complexity for each operation, which is not efficient when multiple random selections are required. Finally, misunderstanding uniform randomness is a critical issue. If your random index calculation is flawed or introduces bias, the selection won't be truly uniform, which is essential in probabilistic algorithms like this one. Ensuring uniform randomness requires careful implementation and validation. Another common pitfall involves incorrectly implementing reservoir sampling. This algorithm relies on precise handling of probabilities, and any error, like using the wrong condition for replacement, can lead to non-uniform results. Beyond these mistakes, there are key insights that can help you excel in interviews. One is recognizing patterns. Many linked list problems have constraints, such as requiring one space or a single traversal. Recognizing these constraints often hints at the need for algorithms like reservoir sampling. Additionally, being able to communicate trade-offs is crucial. For instance, discussing the simplicity of a brute force approach versus the efficiency of a more advanced algorithm shows depth in understanding. It's also important to explicitly address edge cases such as empty lists, single-node lists, and very large linked lists during your solution validation. Interviewers value this thoroughness. Lastly, be prepared for follow-up variations. For example, you might be asked to handle weighted randomness or dynamic updates to the list. Adapting your solution to these extended constraints demonstrates flexibility and problem-solving skills. Finally, let's look at related problems and alternative approaches. Problems like random pick index, random pick with weight, and generate random point in a circle all share similarities with linked list random node, often requiring efficient randomization techniques. Regarding alternative approaches, the brute force method involves storing all node values in an array and randomly selecting from it. While simple to implement, this approach has time complexity per random selection and space complexity, making it inefficient for large lists or repeated calls. A more advanced option is reservoir sampling, which achieves time complexity during initialization and for each random selection. It's both memory efficient, with space complexity, and computationally effective. However, it's more complex to implement and requires a solid understanding of probabilities. Another approach uses an index-based data structure, like an array, for random access. This allows for time complexity during selection but requires space to store the array. Each method has trade-offs, so the optimal choice depends on the problem's constraints and the requirements you're working with. Great work! To summarize, we covered the problem linked list random node and discussed both naive and advanced approaches like reservoir sampling. I hope you found this walkthrough insightful and engaging. Don't forget to practice similar problems and explore other randomness-based algorithms. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!